Hello there again. So let me show you the case, the previous case, the NACA 0012. So here I just finished. I will share this case to you as a reference. So look at what I did was just 4 degrees, 0 degrees, 12 and 22 degrees. So I know this one is installed and I run all the cases. I just duplicate it. Everything is automatically, okay? So this is pretty much what you need to do with your airfoil, okay? You have all the steps, just follow the steps, use the same guidelines I give you. For the moment they're okay, but there's much to do when it comes to mesh, and it's mainly, as I say, related to turbulence. But after running these cases, I just took the data and then I put it in a plot here and just compare the data. So see here that I have the experimental data. Remember, I told you that there is a huge difference between free transition and when you force the transition. In particular, that is related to CD. CL is relative easy. So see that I put here all the cases, even airfoil. Airfoil is natural transition I use here. I didn't use forced transition, and see that I compare everything. So see that pretty much fluent. Here I compute more values, okay? So, but see that pretty much fluent managed to capture very well the maximum CL compared to experimental results. Then airfoil, there are some differences. Even in this slope, there is a slight difference. That's why I'm telling you, I'm not expecting to have an exact match between airfoil and fluent, but we should have similar trends, okay? Here there are many corrections that are entering that airfoils are not taking that into account, and it's not doing the truly physics, but pretty much it's getting good results, okay? So you compare CL, okay? So do it for 3 angles in the linear regime. If you want to go a step further, go and do it after stall or at CL max, and then do the same for CD. This is the tricky one. So here you need to change the scales not to see the figure, but pretty much you see that low angles for tag, you have between all of them good match, and then the differences here. But it's very important also the free transition, forced transition, just to when you compare, okay? So I have all the data there, and this is that is what I'm asking you to do, okay? Pick up your using airfoil that you use in airfoil and then simulate an influent. I just want to show you that you can do much more. So see stuff like this. This is if I would recall, this is a 36 airfoil. I think it's 36 is 215 probably, I don't recall, but this is a transonic or supersonic regime. So here you have shock wave devolution. These are things that the panel methods cannot do that CFD is doing. Okay, so this is why here CFD comes much handy than those panel methods, but panel methods are good also in one stage. And regarding the measuring our domain, in this case, our domain is much larger than I recommend you in the guidelines, okay? So that depends what is your goal, what you are trying to do, but my guidelines is pretty much, let's say that will be the absolute minimum. It can be much larger than that. Also, I gave you the square domain. Look at here that we have kind of this seed topology, okay? So it's up to you, but usually for the moment it's square domain. So you have all the information. So this is the Mach number. Oh, this is the pressure here, but also we have the Mach number. Okay, so I go here, I can choose velocity. Okay, that was temperature, velocity, and then you can measure. So these are stuff that panel method cannot do, and even experiment getting all this data is difficult to have everything in experiment, okay? So is you're following good standard practices, it's pretty much that you are going to get very good results. And just to show you another case, okay, so this is transonic, but now we move to multi-element airfoils. Again, panel methods, they can do it, but airfoil didn't have this implementation. So there are some modifications, corrections to deal with this. So see here in CFD, easily you can deal with multi-element airfoils, okay? And just to show you the mesh in this case, and what is interesting about this mesh, that this is a mesh that is very well done, okay? This is a mesh in particular to simulate transition. This simulation is transition, okay? It's not forced transition, this specific model, because we want to capture here the transition. And when you want to solve transitions, require very fine meshes close to the wall. So let me go here and zoom in, move here. So see that very extremely fine meshes. Okay, so this is using structure measures method. So this is very difficult to do this kind of measures. Okay, you can do it also with ANSYS, but I don't recommend you use this structure method, triangular meshes. And see that in this case it's a square domain that I the one I recommend you, but it's symmetric. Nothing is not different. The important is that you need to avoid strong gradients in the boundaries. Okay, so it's a large box, so there you have that problem. So as we check here again, you have pressure. We can look at Mach number, okay, stuff like that. So these are here many things that you can check that potential cannot get, and also experiments is difficult, okay, to get. Okay, so this is a big advantage in CFD. I'm showing you 2D cases. Okay, no need to say that 3D is the same stuff I'm not showing you, but 3D is pretty much the same. The main difference will be that now you have larger meshes. So just to end at this, I want to show you the finally, okay, just to show you again the workflow, okay, step by step. I'm not going into details, but now I'm going to work with a different airfoil. So see that in this case, we're doing the 6.5 to 10 airfoil, series 6. So just to remind you that you need to have the airfoil coordinates, okay? So here I have my coordinates. I took it. You look for the coordinates where you want, but remember my advice is have split that in top and bottom surface. You give your coordinates there. So you have your coordinate, you go into geometry. Let me open it here. So when you are in geometry, just import it as usual as we did it. You import the geometry, put it here, construct your box, the guidelines I gave you, okay? Then if you want, you can parameterize, okay? You have the rotation there, and then you change it, okay? So you have your geometry. Then, again, with the guidelines I gave you, go to the measure module, okay? So you will import here, you will connect your boxes. And then the mesh model follow my guidelines, and you're going to create your mesh. It doesn't matter the airfoil that you're using. Even if you want to use a multi-element, you just need to have all the coordinates of that airfoil, and that's all. Okay, those coordinates also you can find on the internet. So you follow the coordinate. Remember that you need to create the named selections for the boundary conditions. Okay, this is something that we don't do in potential methods and CFD. You need to do it. So inlets, outlets, top, bottom, and airfoil. In this case, I have a single surface for the airfoil. Okay, I collect everything in a single surface. Even if I import it in as a multi-line, you see that I can select the lines independently. I chose here to have in a single airfoil, but it's up to you. Okay, if you want, you can erase it and do the selections. There is no problem. And then do the mesh following the guidelines. Okay, so in this case, I have also, this is a verified mesh. Okay, here I'm resolving. So probably my y plus here will be less than 1. So you know how to get an estimation. In the boundary layer lectures, probably you will get some more guidelines. I chose not to add the refinement box, but you can have it. Not a problem, it's up to you. And this is your mesh. So after you have that one, go to Fluent, follow the guidelines, and set up your case. Run it for a Reynolds numbers, I think, okay, 3 million is the one that we use in the homework, but if you want to choose a different one, it's up to you. But use a large Reynolds number, 3, 6 millions. And then here I chose different, I chose to run different cases and different tolerance models. Okay, each one will have different behavior, like it probably will give slightly different outcomes. Okay, but let me open, for instance, this one just to show you the setup. It's pretty much the same. Okay, you generate the mesh, import it, go here, then you launch Fluent. Okay, so choose also the number of processors, so that can give you a little bit of speed up, but these are 2D cases, so it's super fast. And then you are in Fluent, and just remember the guidelines I gave you. Follow the vertical tree here. You have this outline view, this tree. Just follow this from top to bottom, and set up your case, and you're ready to go. So it's reading the mesh, setting everything, and we have the mesh here. So always remember, check your quality. Okay, below your mesh quality here. Likely you can get problems like this, but remember, as I told you, it's not a big deal if you get into these values. This is mainly you get low quality just because this is a very fine mesh close to the surface. You can go your improved quality, but this is above, let's say 10 to the minus 6 is okay. This 10 to the minus 5 is okay. So set up here your case, model, okay, choose only play around with viscous model, material, show your working fluid. So for the moment, let's work only incompressible for instance, yeah, like this, but you can put it also compressible. You have many models. Then here in boundary conditions, choose all the named selections that you created when doing the mesh, send the values. Okay, remember to choose reference values to normalize the quantities, but if you want to use forces, it's up to you as well. Methods, as I recommend you, as I told you, use the default method, what is proposed by Fluent, that is okay for these cases. Set up the monitors. For the moment, we just want to monitor CLCD. Then initialize and run your case, and that's all. Then you can do all the plotting here. Okay, so you will have, here in this case, I haven't initialized, I don't have access to the solution, but after you have the solution, you can have there, you can plot pressure, Mach number, and also here you will have the plots to plot, to get the plot on the surface of CP, Y plus, whatever. So this is what you have to do. As you see, it's straightforward, okay? So pick up your airfoil, set up your data, and then follow the steps and do your geometry, your mesh, and run your simulation. So that's all for this. See you next time. Bye.